is chapter 7 in your book. All right. So chapter 7 is all about chemical quantities and stoichiometry. You'll hear the word stoichiometry quite a bit. Stoichiometry is defined as the area of study devoted to the quantities of materials consumed and produced in a reaction. You notice it says in a reaction. So we're going to have reactants and products. We're going to have to talk about chemical reactions. So stoichiometry is not really going to show up today, but it's going to show up in the next videos and some of the later videos for chapter 7. So before we can talk about stoichiometry and using balanced reactions and stuff like that, we have to first introduce some new terms: the mole, molar mass, Avogadro's number, stuff like that. So let's get started with the mole. The mole, abbreviated MOL, 1 mole of any substance contains exactly 6.022 times 10 to the 23rd items of that substance. So for example, if I say I have a dozen eggs, I have 12 eggs, right? Well, if I have 1 mole of eggs, I have 6.022 times 10 to the 23rd eggs. Second example, 1 mole of iron atoms is equal to 6.022 times 10 to the 23rd iron atoms. 1 mole of water molecules, 6.022 times 10 to the 23rd molecules of water. Back to the real world, if I have 1 mole of bananas, I have 6.022 times 10 to the 23rd bananas. Okay, so it's just like a dozen, right? A dozen is 12. A baker's dozen is 13, and 1 mole is 6.022 times 10 to the 23rd items of that substance. And that number is called Avogadro's number. All right. So now I kind of want to talk to you about atomic mass and how we have atomic mass units as opposed to grams per mole. And what we're going to focus on is grams per mole for atomic mass. So at the top of page 2, it says the mass of 1 mole of any element is equal to its atomic mass. So if you look up carbon on the periodic table, you'll see that the decimal number is 12.01 grams per mole. Okay, so as a conversion factor, you can write it 12.01 G over 1 mole, or flipping my fingers, I can write it 1 mole over 12.01 G. So the atomic mass for carbon is 12.01 grams per mole. And that's true for any element on the periodic table. You just go to the element, you find out its atomic mass, it's listed right there, and we are going to use units of grams per mole. Here's an example using atomic mass and using the new term that we've used, mole. Find the mass in grams of a sample of 6 iron atoms. So we're not expecting 6 iron atoms to weigh hardly anything at all, right? Very, very small. Well, just like we learned in dimensional analysis way back in weeks 1 and 2, start with what you're given and put it over 1, remember? So we have 6 iron atoms. And for every 6.022 times 10 to the 23rd atoms of Fe on the bottom, that's 1 mole of Fe. We don't want our answer in moles of Fe, so we have one more step, and that is to cancel moles. So for every 1 mole of Fe, that weighs on the periodic table 55.85 grams. Units cancel, and we're left with 5.5 times 10 to the minus 22nd using sig figs, 6 times 10 to the minus 22nd grams of Fe. All right, next example on this page at the bottom. Find both the number of moles of atoms and the actual number of atoms in a 10.0 gram sample of aluminum. Start with what you're given, put it over 1. 10.0 G aluminum, we got grams on top, right? So for every 26.98 grams of aluminum on the periodic table, that's grams per mole. So I'm basically dividing by the atomic mass here, and I get 0.371 moles of aluminum. Whatever the significant figures is that you start with is generally the number of significant figures you end up with, because everything en route is a conversion factor, and we take those to be exact. In other words, they have an infinite number of sig figs. All right, now we also have to find out the next part of the question. So start with what you're given, put it over 1, 10.0 grams of aluminum. Get that into moles. So 10.0 grams of aluminum times 1 mole of aluminum over 26.98 grams of aluminum. That puts us in moles. And then for every 1 mole of aluminum atoms on the bottom, we have 6.022 times 10 to the 23rd atoms of aluminum. Cancel the units. Remember, when doing this stuff, this is dimensional analysis. Start with what you're given, put it over 1, work left to right. The units are more important because you have to cancel and follow. The last numerator is your answer's units. 2.23 times 10 to the 23rd atoms of aluminum. All right, so the first full example on this, page 3 of our notes, says a silicon chip has a mass of 5.68 milligrams. How many silicon atoms are present? Start with what you're given, put over 1. Milligrams turns into grams of silicon. For every 28.09 grams of silicon on the bottom, I have 1 mole of silicon on top. And then 1 mole of silicon contains 6.022 times 10 to the 23rd atoms of Si. Started with 3 sig figs. My answer is 3 sig figs. 1.22 times 10 to the 20th atoms of Si. Next example. Calculate the number of moles and the mass of a sample of cobalt containing 5.00 times 10 to the 20th atoms of cobalt. Well, first you have to know that cobalt is CO, right? You look that up on the periodic table and you can get its atomic mass. You're going to need it, 58.93 grams per mole. So start with what you're given, put it over 1. 5.00 times 10 to the 20th atoms of CO. We got to get out of atoms and into moles. So I'm dividing by Avogadro's number. You should definitely do this one with your calculator to make sure you get the right answer. You want to know how to divide by Avogadro's number properly. So this converts atoms into moles. You can leave either answer as long as it's three significant figures. You could have had 0.000830 or 8.30 times 10 to the minus 4th moles of cobalt. Practice that one on your calculator. Make sure you get the right answer. All right. Now I want to get to grams, mass. So I'm just going to use moles and I can do it in one step. 0.000830 moles of cobalt times 58.93 grams of cobalt for every 1 mole gives me my answer in grams. Okay. New topic now. So we're not talking about Avogadro's number or moles or atomic mass, but we're introducing something so similar it's almost like it's the same topic. So this is molar mass. So we introduced moles, we introduced atomic mass, Avogadro's number. Now we're doing molar mass. Molar mass is just like atomic mass, but it's for a compound, not an element. So what does it say? It says molar mass equals the mass of 1 mole of a compound, whereas atomic mass was for an element. It's often called molecular weight, formula mass. I'll probably always call it molar mass, but you will read molecular weight quite a bit. Just like an element's atomic mass, for example, 12.01 grams per mole for carbon, compounds and molecules have a molar mass. All right, so if I have H2O, water, I'd have to add up 2 H's and 1 O, right? But we'll do some more examples. We'll do an example right here, actually. Example, a certain chemical dye has a formula C10H6O3. I want to know, in A, I want to calculate the molar mass of C10H6O3. Well, I've got 10 carbons, 6 hydrogens, and 3 oxygens. All right? So it says we'll need to use the periodic table. 10 carbons, 6 hydrogens, 3 oxygens. So there are 10 carbons that are 12.01 each, 6 hydrogens with an atomic mass of 1.01 grams per mole, and 3 oxygens, and oxygen weighs 16.00 grams per mole. If you add these all up, 120.1, 48.00, 6.06, you get 174.16 grams per mole. That's how much 1 mole of C10H6O3 weighs. All right? So B asks us the next question. That question says, how many moles of C10H6O3 are contained in 1.56 times 10 to the minus 2nd grams of the dye? So we're just going from grams to moles. Okay? And we did this in the last few pages. Start with what you're given, put it over 1. I have 1.56 times 10 to the minus 2nd grams of C10H6O3. If you want to call it 0.0156, you can. In fact, I probably would have. Now I have grams on top when I start, right? So for every 174.16 grams of C10H6O3, that's per mole, my answer is 8.96 times 10 to the minus 5th moles of C10H6O3. Okay, so some homework problems from chapter 7. This is number 3B. So it says, calculate the number of SO2 molecules in 1.28 moles of SO2. So 1.28 moles, you start with what you're given, put it over 1, and to get from moles to molecules, we have to use Avogadro's number. And I see that I have to have 1 mole for every 6.02 times 10 to the 23rd molecules SO2. Okay, so started with 3 sig figs, my answer is 3 sig figs, 7.71 times 10 to the 23rd molecules. 7.4a, calculate the number of lithium atoms in 4.5 moles of lithium. So I start with what I'm given, put it over 1, 4.5 moles of lithium. For every 1 mole of lithium, I have 6.02 times 10 to the 23rd atoms. Started with 2 sig figs, my answer has 2 sig figs, 2.7 times 10 to the 24th atoms. Now notice the difference between molecules and atoms in 7.3b and 7.4a. That's because SO2 is a molecule, whereas Li was an atom. So 7.4d, calculate the moles of C2H6 in 3.75 times 10 to the 23rd molecules. This time I'm starting with molecules, start with what I'm given, put it over 1. Because I'm starting with molecules, now I have to have Avogadro's number on the bottom. For every 6.02 times 10 to the 23rd molecules of C2H6 on the bottom, there are 1 mole of C2H6. Started with 3 sig figs, my answer is 3 sig figs, 0.623 moles C2H6. Make sure you can replicate 7.4d on your calculator. Sometimes dividing by Avogadro's number is difficult for some people. C, this is 14C. Wasn't assigned, but you have a lot of problems like it. Calculate the molar mass. Anytime you're asked to find the molar mass, you just add up all of the elements that you see in the formula from the periodic table. And as you can see, I like to report my molar masses to the hundredths place, like the last answer was 183.00 grams per mole. Top of page 2, this is number 11 from chapter 7. It wasn't assigned, but it's very similar to the ones that were. So chapter 7, number 11C, find the molar mass of Mg3PO42. Notice the parentheses around PO42. That's going to give me 8 oxygens. Be very careful. So I add all this stuff up. I got those numbers from the periodic table, and Mg3PO42 weighs 262.87 grams per mole. Again, I like to report my molar masses to the hundredths place. So this is chapter 7, number 22. D says, calculate the mass in grams of 0.145 moles of C2H6O. So I need to go from moles, that's my start with what I'm given, put it over 1, moles to grams. To go from moles to grams, or grams to moles of the same substance, we use the periodic table. So I start with what I'm given, put it over 1.145 moles C2H6O. Now for every 1 mole on the bottom, we have 46.08 grams C2H6O on the top. You notice on the right there with the little writing, it's 46.08 G/mole. But when you use dimensional analysis, to start with what you're given, put over 1 and move left to right, it's grams all over 1 mole. So be careful on that. Whenever I start with 3 sig figs, I end up with 3 sig figs. The answer is 6.68 for number 22. 26D, calculate the number of moles in 308 grams of BaSO4. All right, so now we're just going the other way. This is the opposite of 22. Start with what you're given, put it over 1, 308 grams, and now I got to get into moles. So for every 233.37 grams of BaSO4 on the bottom, I have 1 mole of BaSO4. It's very important to write out all your units when you start with what you're given, put it over 1, and move left to right. You're following the units more than you are the actual values.